Okay. Yeah, IceCube-PINGU. The new, let me see. Yeah, the proposed extended experiment for IceCube. Yeah. So thank you for introductions and for the organizer for giving me the opportunity to present our recent work in this conference. And these are the titles and the reference and my collaborators. And this work I'm going to test whether we can using the neutrino test on South poles to test the dark matter self-interactions by the method of the galactic dark matter being trapping inside the sun. Okay. So this is the outline. First, I give you the motivations why we need dark matter self-interactions. Then how this dark matter being accumulated inside the sun. Then give you the numerical and the parameter space. Then how the sensitivity for this proposed new experiment to this dark matter self-interaction. Then I give you a brief in conclusion. Just thanks from the first speakers. We know that the dark matter there's a firm evidence for dark matter existence from different experiments and different reports of universe evolution. So we can say our best knowledge of dark matter comes from experimental measurements, not from the theories. Theories, we have infinite possibilities to show. So first, this is our solar system inside our galaxies. So this is the velocity distribution, rotation velocities. So this tells us we are inside the dark matters. So this message gives us we can test, we can measure, we have an opportunity to measure dark matter on the on the Earth. So we can prepare the experimental undergrounds, you know the stories. Then we can test whether the dark matter can collide with the target or precisely the nuclei we prepare in the experiment. So this is the so-called money plot for the dark matter experiment. We call this is the direct search for the dark matter, and the different experiments, different nucleons give you different sensitivities. And you can see the interesting part is the sensitivity is lost as long as the dark matter mass is so smaller than 10 GeV, roughly. This is due to the nature of the weight of the nucleus. So we cannot do better than this. So my interest in this talk is I concentrate on the dark matter mass, the low mass region between the 1 to 10 GeV using an indirect way, and test the dark matter self-interactions. And this is the indirect search. The best constraint you can see is from the IceCube, not a PINGU, the IceCube experiment. Just to give you some feeling for comparison between the direct search and indirect search. And why the dark matter self-interactions? First, there's the ambiguity or inconsistency between the observations and numerical simulations. So people can do the dark matter galaxy formations from the computer. They call this the n-body simulation, and they put this the assumption dark matter that collisions means they don't interact with each other, and they have a so-called cost and core problem. They found for the small scale in the galaxies, the dark matter density is growing, and its density like R go to minus gamma, and gamma is about 1.8 or 2. So there's a cost structures for the simulations. But what we observe is this is the velocity. So the observation from the experiment from the sky, we see the dark matter for the small scale, the density is around constant, that R equal to minus gamma. And people using people worry about uncertainty from the sky, so they're using the Milky Way, which are nearby, and choosing a small size for this the galaxies or the small baronic retreat, because they just tried, because I will tell you that simulation is the ambiguity you have to keep in mind is probability is the simulations, they put the dark matter only. But what we see from the sky is from the standard model of the luminous components. So this simple reason tells us how this ambiguity come from. So they just try to lower down, suppress the uncertainty. So they're choosing the most contents for dark matters for those galaxies, and they compare how this compare with the simulation. And again, they tell us the cost, like the structures being ruled out about the 99 or 96%. So that's one. And I already tell you, there's the cosmology embodied simulation consider only dark matter only, but observation from the baryons. So that could be just the lack of understanding between how the baryons interact with dark matters. Of course, dark matter self-interaction is one of the solutions to resolve this ambiguity, but just bear in mind that there's many unknowns in this field. Then another inconsistency is called a missing satellite. We have a galaxy halos, and from simulation we also have a sub-halos surrounding this galaxy halo, and those sub-halos are being treated as the seeds for the small galaxies. We call this the satellite galaxies. And just from the simulations, there are a lot of sub-halos compared with what we observe. So there's some missing part. Why only part of sub-halos can form into the galaxies, or we just don't have that many sub-halos from simulation, and this is inconsistency from data. Then the third is so-called too big to fail. Usually we just naively thinking there's if you have a denser dark matter areas, it's more easier to attract stand up the particles together and form the galaxies. However, we found if the sub-halo is too dense, then we never found this kind of a galaxy, this kind of a sub-halo to form into a galaxies. So the black holes are too big to fail. If a dark matter sub-halo is too dense, it cannot go to form the galaxies. So that's the motivation for the dark matter self-interaction. If we have dark matter self-interaction, those problems can be solved. Just one of the solutions. Okay, then if we have dark matter self-interactions, this is the constraint. First is the Bully cluster. It's the famous evidence for dark matter. You just see the two clusters, they collide, and the mass centers on the dark side and the amount of gas is prevalence. And this Bully cluster is true. The dark matter self-interactions over the dark matter mass. If it's larger than 1 with this unit, the self-interaction is just too strong and being excluded by this experiment. So if dark matter have self-interaction, it should be smaller than this one and larger than 0.1. The reason is if dark matter self-interaction with this first mass ratio is less than 0.1, then you don't see this effect from the simulation. So the dark matter self-interaction will be within in this regime. Then we study the dark matter being captured by the sun. So there's a galactic dark matter distributions, and they will pass through. They go to the sun, and they will interact with the nucleus inside the sun, and they will be stopped, or they will be their velocity will be slowed down. Then if the final velocity of dark matter is slower than escape velocity of the sun, they can be trapped inside the sun, and that's the main ideas to accumulate or to capture the dark matter inside the sun. There's basically 3 mechanisms for dark matter density inside the sun. First is the capture. I was already explained for the dark matter coming in collide with the nuclei of the sun, then they can be slowed down, and less than escape velocity, they've been captured. The second one is called evaporation. Those been trapped inside the sun dark matter, they still have an opportunity to collide with the nuclei of the sun. Then, if the after scattering, their final state, their velocity is larger than escape velocity, they can be kicked out. Although they have been trapped, they can be kicked out. Then we call this is evaporation. The other is the annihilation. Because we have a more dense dark matters, then they have a chance to meet each other, then annihilation into the standard model particle, and they will disappear. So in the end of the day, the dark matter numbers will be equilibrium for these three mechanisms, or these three processes go to they balance each other. However, in our study, we consider more complex than this, since we consider dark matter self-interactions. So we have dark matter self-interaction captured due to dark matter self-interaction. This is the following. The dark matter already been captured inside the sun, and they can be interact with the galactic, the dark matter from the galactic, and they can slow down the galactic dark matter and capture it. And the evaporations due to the dark matter self-interactions, they put the two trapped dark matters inside the sun, and they can be kicked up, and one of them is go out, is larger than the escape velocity, and they will go out like following. So this is and for the dark matter nuclear interactions, there's two types. The one is called a spin independent, the other is due to the spin dependent part. It just depends on the nuclei spin. For the spin independent, they're just proportional to the atomic numbers of a nuclei. And the evaporations, I already tell you the mechanism. They can just larger than escape velocity and can heat up. And you can imagine the evaporation effect is the relevance for the low mass, because the low mass, they can be easily larger than the easily being kicked out from the sun. And we assume the dark matter form a core inside the sun once they've been trapped, and their density distributions is isothermal. And this is the gravitational potential of the sun. And here we assume the dark matter is thermal equilibrium with the sun, core of the sun. You can imagine the dark matter core is about 1% to 10% size of the radius of the sun. You can estimate this easily. And this annihilation, dark matter annihilation to standard model particle, and then disappear. Dark matter's self-interaction has been helped to trap and evaporations. Okay, so this is just formulas for what I just explained. Okay. We don't go to detail, just calculations. So we have a dark matter number density with the time, and this is capture rate, and you can set this is a self-interaction capture and evaporations and annihilations. So this is proportional to the number density of dark matter inside the sun in a square. You can solve this. This is dark matter numbers inside the sun, and this tau A is the characteristic time for the dark matters. So and you compare with the life of the sun. So once this equilibrium time is around 1, we have the saturate for the dark matter numbers, and this is if dark matter being captured to be saturated, this is the numbers. And this is the parameter space we scanned. For the small regions is the non-equilibrium in number. So we can see for a large number of parameters, the dark matter is allowed to be captured within the lifetime of the sound. That one is for spin dependent. This one is for spin independent. This dashed line is the current bound from the direct search. Oh, I just remind you in direct search. So these figures tell you the dark matter self-interactions with the captured total number. You can see the dashed line is without dark matter self-interactions. So with the dark matter self-interaction, there's two effects. First, you enhance the total numbers of dark matters. This is important because if you have more dark matter, then your annihilation, you have more events to be seen at the south pole. So that's the reason we can test and increasing the sensitivity. The second is you can see there's a peak length drop. This is due to evaporations. Because dark matter is too light, they cannot be trapped anymore. They just been easily be kicked out, and the final stage just easy to larger than the escape velocity. So we call this the turnover point evaporation mass. And you can see with including the dark matter self-interactions, the evaporation mass is increasing, but the total number is increasing. It's also increasing. So you have the two effects. You can compare. It's different parameter space, but that's the feature. Then we define the dimensionless quantities, defined from a different effect. I just explained. We have a 5 effect, and so the quantity, dimensionless quantity R, just tell you the competition between evaporations and the self-interactions. Basically, that's the idea. And this dips due to this cancellation from the CS equals the capture due to the self-interaction and the evaporation that equals. So for these regimes, the R larger than 1, this regime is dark matter self-interaction dominant. 1. So this is the regimes for the dark matter dominant. You can see that they are large. They have a large parameter space that you can. This is experimentally interesting parameters. So within these regions, the dark matter self-interaction is non-negligible. That's the point. So now I go to how to connect to the PINGU. The PINGU name is the Precision IceCube Next Generation Upgrade. And this is IceCube. The size is about 1 cubic kilometers. This is the largest neutrino telescope so far. They're using the ice as the medium, as a target, as a chunk of mediums. So the neutrino comes collide with the hydrogens, or the protons with the waters or ice, and they have a triangle radiation that being captured, and the light can be captured by photon multiplier of this string. And the PINGU is the small size inside here. So this IceCube, this is deep core, and the PINGU is here. So you can imagine a smaller size, you are sensitive to the smaller energies. So the PINGU is sensitive to dark matter mass is around 1 to 10 GeV. That's our interesting regions. And our events, our signal come from dark matter annihilations into neutrino. We consider neutrino because neutrino, they just transparent. They can just directly escape from the core of the sun come to here. And we consider 2 channels, dark matter annihilation to tau and neutrino directly. The reason we don't consider mu is because mu, what's mu? Because lifetime of mu is longer, so dark matter annihilation to mu, the mu have a chance to interaction with the nuclei inside the cell, and they will lose energy. And once the lost energy, that decays to neutrino. Neutrino energy spectrum is softer, and softer neutrino spectrum, they will have a larger atmospheric neutrino background. So which we don't consider. We have to consider only these two channels. And this is annihilation. So annihilation is just n squared. So we have a dark matter numbers previous, and this is n squared times the annihilation rate. Again, you can see including the dark matter self interaction, we can enlarge the signal several orders. So this is the spectrum, the dark matter being annihilation, this dark matter flux annihilation, and we consider the flux, the oscillations in the sun or in the earth, also in the vacuums, from the travel from the sun to the earth. And annihilation rate, the flux divided by 2 pi r squared, and the branching ratios. And this is a total number neutrinos spectrum. And this is effective areas. They come to the IceCube, and this is just IceCube effective values for different flavor of a neutrino. So this is electron neutrino, this is muon neutrino, responsive effective values, and this is efficiency for different flavor neutrino. We're just using these numbers. And that's the background from the atmosphere. We assume 5 years to significance. Also, because from the sun, and we have to consider the open angles from the IceCube to the sun. So we consider the daylight within these angles, and with the angular resolutions around 10 degrees. This is just from the experiment. And that's our result. You can see the shadow regions. This is the dark matter. The vertical line is dark matter self interaction. The shadow region is excluded by the Boole cluster, and the dark line here, below this one is just the dark matter self interaction, just too small to have any effect from simulations. So within this range, these two orders are really the interesting part from the simulation and observations. And this is our sensitivities by the PINGU from this channel, Kai. And this is spin dependence. We take these two numbers, and you can see the sensitivities. They can almost cover all range from the actual physics and the simulations. And you can see we lost the sensitivities just below the evaluation max. Yeah, since because below that we cannot capture any dark matter. And this different channel, this tau channel, again, we can cover most interesting parameter and the sensitivity range and the spin independent of similes. One point here is the signal here is dark matter annihilation to non-model particle. And usually this is, if dark matter is thermal radius, then we have a so-called sigma A from the standard cosmology textbook. We know this is the WIMP, interesting range. And naively you were thinking, if the annihilation rate is larger, you have a more chance, more signals. But here, you have the green light is smaller annihilations. This is 3 times 10 to minus 27. This 3 times 10 minus 26. So if it's green, you have, if the annihilation rate is smaller, you have a better sensitivity. So this kind of anti-intuitions. So I go to the conclusion. We solve the general dark matter evolution equations, including the dark matter self captures the capture rate due to the dark matter self-reactions and the evaporations due to the dark matter self-reactions, which are not considered before. And the dark matter self-reaction is significant within the range 1 to 10 GeV. That's the range we consider here. And dark matter self-reaction will enhance the total numbers in traffic and further increase the event and then increase the sensitivities. For example, heat, in this case, PINGU. And dark matter self-reaction will help to reach equilibrium quicker. This equilibrium, not thermal equilibrium. This is just a number equilibrium, which means that the capture rate equals to the annihilation rate. And the dark matter self-reaction we have shown is tested. That allow regimes from the actual physics simulations is testable and it's almost covers. We cover almost the most interesting parameter space from PINGU. So we hope this will help us to further understand the property of dark matter. Thank you. This is my talk.
Any questions?
Yeah. Sorry, just like a comment. So
yeah.
If we look at the parameter and stem model, KIAS-NCTS stem model,
yeah.
It's mediated by very heavy particles.
Yeah.
You can write down KIAS stem model. If I require this one to be require the parameter to be thermally reproduced, it's 3 times 10 to the minus 26 Ca³ per second. Right? This one's S channel. And I can, in principle, I can locate this like E channel. So
then that would become the direct search. That's your point?
No, I mean, that kind of concern will be
right.
Will be kind of stronger, I would say.
Right.
Self-energy is
right.
about 10 to minus 20 something.
Yeah. Yeah.
It's quite large.
Yeah. Yeah, it's quite large. Right. Yeah. Yeah. Actually, I would treat this as a theoretical motivation, which I didn't mention here. Yeah. So if you can be accurate, you can lose the connection between you just saying the rotation, the two diagrams, by assuming the media is the mass of media is smaller than the dark matter, and you allow dark matter annihilation into the media, and you relax the constraint. And the case is like following. Then you probably you have a stranger constraint from direct search. I mean, if a direct search, you don't have any signal from the direct search, and in that case, the indirect search still provide you opportunity to see the signal. That's the point.
Do you have an estimate of how much parameter will be in the sun?
Yeah, it's about let me think, 10 to 40. It's about 10 to 40.
Compared to the mass of the sun.
Compared to mass.
Yeah, of the sun.
Even the total mass.
Yeah.
Oh.
Would it be a significant proportion? Or
the first is we don't know the dark matter mass exactly.
From
my
some constraint of
yeah, it's about 10 to minus 10 to 12 of the solar mass. It's quite small.
Okay.
So if you treat the number is about 1 nucleus capture 10 to minus 10 to 12 dark matter. But because dark matter
all these are model dependent, but then it's anyway small.
This is not really model. This is quite model independent. Yeah. Because only depends on very few assumptions. But that's a detail.
Yeah, I mean, just I mean, this would also have an effect on pulsar, for example.
Yeah.
And
yeah.
So
You can apply all these from different solar
different compact systems.
Yes, compact systems.
And then you can observe the period color field change on the.
Yeah.
So do people search for those kind of things?
Yes, few people. And also you can apply to the Galaxy Center and you assume some.
So they experiment looking for those.
Yeah.
So okay, let's I think let's thank